Every now and then, an idea takes form that changes everything. It revolutionizes the way we see and understand the world around us. I believe that just such an idea took form in the medieval Islamic world. It's the idea that everything, from the stars above to the workings of our own bodies, is not arbitrary or whimsical, but subject to certain systematic rules. And what's more, that we humans can work out what those rules might be. And then we can refine and test our theories through observation and experiment. In other words, it's the idea we now call the scientific method. For me, the story of the scientific renaissance that took place in the medieval Islamic world is a personal one. This is my cousin Samir's house in the Iranian capital, Tehran. I haven't seen some of the relatives on my father's side of the family in over 30 years. This is my not so tall but very beautiful Auntie Anisa. The Al-Khalili family is originally from the city of Najaf in Iraq, south of Baghdad. In fact, I grew up in Iraq. But when Saddam Hussein came to power, the family split. Many of the Al-Khalilis fled here to Iran. As my mother's English, I came to Britain with my parents. There, I pursued my passion for science, and am now a professor of physics at the University of Surrey. But now, I find that my own scientific work and my Arabic and Islamic heritage are intertwined. On my journey through the Middle East, I discovered that an astonishing leap in scientific knowledge took place here 1,000 years ago, under a powerful and flourishing Islamic empire.
Wealthy, powerful, successful cultures will produce enormous advances in understanding and in technique. And that's just what we find in Islam, in Baghdad, under a series of successful, powerful, wealthy, and self-confident Islamic regimes.
Over 1,000 years ago, the Islamic Empire was the largest in the world. It governed an estimated 60 million people. That was over 30% of the world's population. I found an archaeological fragment of this glorious past in a suburb of Tehran, not far from my cousin's house. These ancient walls, tucked behind a back street on the outskirts of southern Tehran, are literally all that remain of the ancient city of Ray, the city that the great Persian geographer Al-Muqaddasi described as one of the glories of Islam. Of course, Ray was just one of a number of cities that flourished under early Islamic rule. From Baghdad, its capital, the empire spread across thousands of miles, from North Africa through to Central Asia. Cities like Al-Askar, Basra, Merv, Gurganj, Bukhara, each powerful and thriving cities. Each would have been rich in trade, alive with culture. Each would have had its own libraries, its own academies. These were powerhouses of the new science. This really was a golden age.
Think of that span of land. This is larger than any empire human civilization had ever known. Within that span of land, you can plug in the Roman Empire and it will fill just maybe, what, 1/3 of it, 1/2 of it, or something like that.
Reminders of this great Islamic empire are everywhere in the Arab world today. This football match in the Syrian capital Damascus is being played at the Abbasid Stadium. That's the name of the family who ruled the Islamic Empire from from 750 to 1258 AD.
هذول اجوا بعد عهد الأموي وعملوا حضارات بناء.
This large territory allowed them to raise enormous tax revenues to fund a search for knowledge and scholarship, which became known as the translation movement. They sent scholars around the known world to gather up great books and have them translated into Arabic. It's a legacy that's still alive in the minds of most modern Arabs.
جماعة اهتموا بالفكر بالفلك وقدموا يعني طوروا تقويم الشهر كمان وعرفوا الكتب اليونانية واهتموا بالعلم كثير بالطب وبالهندسة وكل
For medieval Islamic leaders, scientific knowledge was crucial to successfully running a vast empire.
They did have a big and sophisticated governmental administration, and obviously that needed knowledge. If you wanted to be an administrator and you had to assess taxes, you needed to know about mathematics. It also wants to be able to build monumental buildings. That requires the knowledge of architecture and, again, mathematical skills to construct fine buildings safely. Medicine, just to keep the elite happy and healthy. And those are the areas of knowledge which are first translated from other languages into Arabic.
The legacy of the medieval Islamic empire is scattered across a vast region. There's architectural masterpieces like the Umayyad Mosque in Damascus, the Jami' Mosque in Isfahan, and Al-Azhar University Mosque in Cairo. And then there are many ruins that still hint at past glories, like this, a crumbling 8th century palace deep in the Syrian desert. And this, a huge Muslim palace called Medinat al-Zahra, currently being excavated in southern Spain. These are the impressive ruins of Medinat al-Zahra, the fantastic palace city built outside Cordoba in the 9th century by Abdurrahman III, who was the greatest of all the Andalusian caliphs. At the time that it was ruined, Cordoba was in fact the largest and most important city in Europe, a rival to Baghdad in the east for a center for Islamic scholarship and science. And as I traveled, I saw how science, especially numerical record keeping and measurement, was crucial to dealing with the challenges of running a vast empire. This is the mighty River Nile as it flows through the Egyptian capital, Cairo. Since antiquity, its unpredictable floods have determined the fate of Egypt's people, bringing years of lean and plenty. By the 8th century, Cairo was part of the Islamic Empire, and the new rulers took the first step to understanding this mighty river in a scientific way. They built a device to measure it.
Amazing structure, right?
Dr. Nader Al-Bizri of the Institute of Ismaili Studies is showing me the Nilometer. It's basically a huge colonnade that was built in a chamber connected by tunnels to the river. As the water rose or fell, its height could be read from the central column.
The central colonnade here is ultimately a measuring instrument. It is very precise. It's almost 1 inch between a marking and another.
Presumably they need to know seasonal variations in the height.
And to try to have some sort of record so that they could measure against certain years, where a year was known for a high level of flood versus another year known for its drought. Then they might perhaps take some precautions.
Yes. The data collected from the Nilometer did have one practical use. By creating an objective record of the river's behavior,
It allowed the rulers of the time to calculate how much tax to levy on Egypt's farmers. But whatever its uses, what I love about the Nilometer is how it shows that to understand the world, you have to build devices to measure it.
If you think very hard, it's never obvious that measurement can make sense of the world around us. The world appears, as a Western philosopher once put it, like a buzzing, blooming confusion. And the idea that we as a group have tools which are reliable, which have sufficient integrity, which have an intellectual grip that can make sense of the basic phenomena we see around us, that's an astonishing idea.
And one medieval Islamic ruler made measurement a personal obsession, giving it a scale and ambition that was truly unprecedented. His name was El-Ma'mun, and he became the caliph or ruler of the Islamic Empire in 813 AD. El-Ma'mun lived in a culture without portraiture, so all we have are later impressions of what he might have looked like. El-Ma'mun funded a range of scientific research, but one particular project was a personal favourite of his. And given that he ruled over such a large territory, it's hardly surprising what it was: map-making.
In the second decade of the 9th century AD, El-Ma'mun commissioned a new map of the world, and his scientists did a pretty impressive job. It was a vast improvement on all maps that had come before. What we see here is that they've really got the Mediterranean, its shape and how it links in with the Black Sea, the Middle East, even the whole of Asia as far as China and Japan. They've even got the Indian Ocean and the east coast of Africa. It all looks pretty impressive for the known world at the time. Of course, what El-Ma'mun ultimately wanted to know was how much of the Earth as a whole did he possess? And this begged the question, just how big is the Earth?
It's a sign of amazing ambition that groups of scholars and craftsmen together can, as it were, capture the world. Where does that ambition and that confidence come from? Part of it comes from religious faith, because the world was made by someone a bit like us, but much smarter. If we're smart enough, the thought was, we could probably make sense of a bit of what he did. And that's very clear as a motivation in a lot of Islamic, as in a lot of Christian science.
And more specifically, the practice of Islam demanded that its followers have a very clear idea of the size and shape of the world.
Now, this is crucial information for Muslims, because wherever they are in the world, they need to know the direction to Mecca for their prayer. This is known as Al-Qibla. Now, over such a large territory, finding the direction to Mecca is not a trivial problem.
This problem was wonderfully illustrated when a mosque was built recently in Washington, D.C. Some worshippers were confused because the direction they were told to face when praying was slightly north and not southeast as they expected. After all, Mecca is southeast of Washington, and on a flat map, it does appear to lie in that direction.
But on a curved sphere, the shortest distance between any 2 points follows what's called a great circle. So, for example, this great circle line between Washington and Mecca is quite different to what you might expect. So the direction to Mecca from Washington actually points slightly northeast rather than southeast. Of course, this is complicated stuff, but the key point for Islamic scholars is that knowing the direction to Mecca requires a knowledge of how steeply the earth curves. And that means knowing how big it is.
So El-Ma'mun commissioned his very best scientists to measure it.
Hello.
Hello.
Professor
How are
Sami.
you?
I'm Jim Al-Khalili. Nice to meet you.
To understand how they did it, I'm meeting up with Professor Sami Chaloubi from Aleppo University in Syria, who's an expert in early Islamic
Come and
science.
join me.
إلا عندما قسم هاي على 7.5 عندما قسمها على 7.5
Professor Chaloubi began by explaining the measuring technique, which El-Ma'mun's scientists first used and which they had inherited from the Greeks.
We're now talking about the earlier
Yes.
Aristophanes technique of measuring the circumference. It was repeated again by the Abbasid astronomers, was to measure the distance between 2 points and then look at the angle of inclination of the sun. So in Egypt, in Aswan down in the south, they regard the sun as being vertical. This is near to the equator. And they worked out how far away from the vertical the sun was if they measured it from the north of Egypt in Alexandria, which is on the Mediterranean coast.
El-Ma'mun's astronomers repeated the Greek experiment in Syria and Iraq by measuring the angle of the sun in the sky at noon at one known location. They then walked due north to a second location, carefully measuring the distance they travelled. At the second location, they once again measured the angle of the sun at noon. This angle would have been slightly smaller than the first one. With these figures, El-Ma'mun's astronomers were able to estimate the Earth's circumference. They got a value of 24,000 miles, within 4% of the correct value. Not bad, you might think, but this method was flawed and ultimately unreliable. The main problem with it was that measuring the distance between two locations was incredibly difficult. It could only be done by the unreliable method of counting paces as you walked through the burning desert. A more reliable and sophisticated method for estimating the Earth's size was needed, and 2 centuries after El-Ma'mun died, it came. What made it possible was a great leap of imagination, and the fact that by 900 AD, much of the world's mathematical knowledge had been translated into Arabic, so scholars could scrutinize and improve on it.
Out of this obsession with scholarly learning came a true mathematical visionary, Abu Rayhan Muhammad ibn Ahmed al-Bayruni. And like all Islamic scholars of the time, al-Bayruni was obsessed with the science and mathematics of the ancient Greeks, Babylonians, and Indians. And because of the success of the translation movement, he had literally on his desk the great work on geometry by Euclid, Ptolemy's Almagest, the Indian text, the Sinhind, and the famous work on algebra by Al-Khwarizmi.
كان مكتوبة كتابة كتابة حطوا ورقة.
Professor Chaloubi has brought along the book in which al-Bayruni describes how he combined algebra and geometry with some very simple and practical measurements to solve the epic problem of how to calculate the size of the Earth.
بيروني the text from
This is
this
his
القانون المسعودي.
the Mas'udi canon.
Yes.
This is Bayruni's canon, which I've been trying to get hold of, where he describes this fantastic experiment. And, oh, you found the page?
Yes.
Having read al-Bayruni's description of how to estimate the size of the world, I wanted to try it for myself.
First, he had to find a fairly high mountain from the top of which he could see a flat horizon. In this case, the sea.
What I love about this story is that with a few simple measurements around this small mountain peak, you can work out the size of the whole world. Al-Bayruni's first step was to work out the height of the mountain. He did this by going to 2 points at sea level, a known distance apart, and then measuring the angles from these points to the mountaintop.
So, to measure the angle to the mountaintop, Bayruni had to use a device like this, called an astrolabe. It's basically a giant protractor. It has the angles in degrees marked around the outside, and a pointer to help him determine his line of sight. So if we try now and determine the angle to the top, it has to hang freely, and then, okay, so if you let it hang.
I'd like to stress, if you haven't noticed already, that Al-Biruni would have made his measurements more meticulously than I am. He did them again and again to get consistently reliable results.
Okay, that's about it. And that is 24.5 degrees. Okay, so now we've determined one angle. We now have to go and pick our second spot along the beach.
The distance from the first to the second point must be measured accurately. In this case, it's 100 meters, and the 2 points must be in a straight line with the mountain. I measured the second angle to be about 26.5 degrees, and now had enough information to calculate the height of the mountain. Using trigonometry and algebra, Al-Biruni used a formula that relates the height of the mountain to what are known as the tangents of the angles he measured. Using my measurements, I get a figure for this mountain of about 530 meters. I now need only one more measurement to get the size of the Earth. And to get that, I have to climb to the top of the mountain.
What Biruni did next was measure the angle of the line of sight to the horizon as it dips below the horizontal. So we're going to try and reproduce that. So if you can lift it up so that it's hanging, and if I locate the horizon, okay, which is about 0.5 degree, which is about the value that Biruni got. Now here's the really ingenious part. Biruni had measured 4 quantities, 3 angles and a distance. He used 2 of the angles and the distance to work out the height of the mountain.
Al-Biruni now had everything he needed. In essence, Al-Biruni imagined a huge right-angled triangle which has as its 3 corners the mountaintop, the horizon and the center of the Earth. Trigonometry told him that the angle he had measured and the height of the mountain are related to the radius of the Earth, and algebra allowed him to calculate it.
With this formula, Biruni is able to arrive at a value for the circumference of the Earth that's within 200 miles of the exact value we know it to be today, about 25,000 miles. That's to within an accuracy of less than 1%. A remarkable achievement for someone 1,000 years ago. For me, Biruni's experiment is an early dramatic example of a scientist using mathematical reasoning to extend humanity's reach. He really pushes the idea that abstract geometrical rules governing idealized shapes like perfect circles and triangles can help us to comprehend the real world. Einstein used precisely the same approach, admittedly with much more advanced mathematics, when he developed his general theory of relativity almost 1,000 years after Biruni. But both Einstein and Biruni were united by a single common idea. With mathematics, humanity can embrace the universe.
In this story of the birth of the scientific method, the Islamic scholar's ability to master sophisticated mathematics is the first crucial ingredient.
The second crucial ingredient is the use of experiments in science. Without experiments, theory remains meaningless and sterile. It's experimentation that allows theory to be held up against the real world. It gives it physical meaning. But whereas sophisticated mathematics grew out of the empire's obsession with the world's learning through the translation movement, practical experiments came from the daily needs
of a powerful and expanding civilization. The driving force of the expanding medieval Islamic empire was trade. It boomed from around 700 AD onwards, creating a massive demand for metal workers, glass blowers, tile makers, craftsmen of every possible kind. When this collided with scholarly tradition, symbolized by the translation movement, it had seismic consequences for science.
The sciences absolutely depend, astronomy is a wonderful example, chemistry is another, on really intense relationships between craft traditions of instrument making, of working with metal and fire, of working with medicines, drugs, plants, and scholarship, highly sophisticated literary and mathematical analysis. And the Islamic world is just such a place.
By around 800 AD, the great cities of the Islamic Empire dominated the world's trade. To its markets came silks, spices, drugs, fruit, perfumes and gold, from as far afield as India and China in the east and Spain in the west. Anything that could be traded was. A wonderful relic of this medieval trade boom are the great caravanserais, like this one in the Syrian capital, Damascus. This huge vaulted building was designed as a resting place for all the traders and their animals who visited the city. On their ground floors were wide spaces for animals and goods. And above there were rooms for the rich merchants to refresh themselves before another day of haggling. One 10th century traveller talks of the riches and beauties of the bazaars, and that the income of the provinces and localities was between 700 and 800 million dinars. Markets like this in the Egyptian capital Cairo still capture the intensity of medieval trade. And still surviving in the modern world of the internet and the mobile phone is a fantastic example of how traders 1,000 years ago communicated across a vast empire.
So this is a carrier pigeon, its base is here, so wherever you took this pigeon all over Egypt, it will make its way back to this guy. There's a famous story that a rich Cairo merchant by the name of Anur wanted to grow cherry trees, so he sent a message with a carrier pigeon to a contact of his in Damascus asking for some seeds. His contact sent back 500 birds, each one carrying a small bag with seeds in it. The whole process took just 3 days. Sort of a medieval FedEx, really.
By 700 AD, the Islamic Empire was taking the first steps towards mass production. And in this world where knowledge of materials, metals, and how they're worked became increasingly important, one practice flourished. It's the practice that was inextricably linked with magic. Specifically, the dream to turn base metals into gold. The mysterious practice of alchemy.
The ancient art of alchemy was a mystical system of belief based on spells, symbols, and magic. But I believe it took Islamic scholars to turn this quasi-religion into something much more scientific. Chemistry.
Increasingly, the knowledge of the alchemists found more and more practical applications. For instance, when, during the last decade of the 7th century, the ruler of the Islamic Empire, Abdul Malik, made the bold decision to create a common currency for all his dominions, he turned to alchemists for help.
The proportion of gold to other alloyed metals that you have to put into the dinar to make the dinar usable. Otherwise, pure gold will become very soft and you can't use it. So that proportion is adjusted by, believe it or not, in this period, the alchemists. It is the alchemists who knew how to combine metals together and how to get the proportions of this gold to silver and gold to bronze and so on.
السلام عليكم. أهلا وسهلا. كيف الحال؟
I hunted down tangible evidence of the skill of medieval Islamic alchemists in the old markets in the Syrian capital, Damascus.
This is an Islamic dinar. The date of this is 128 after Hijri.
So the middle of the 8th century, almost 740s.
Yeah, in the middle of the...
This 1300-year-old coin, made of an alloy of different metals, isn't just durable. It's also malleable enough to be inscribed with intricate Arabic writing.
No God instead of Allah.
Coin making is one of the many examples of how the practical needs of a booming economy began to turn the magical practice of alchemy into modern chemistry.
What's striking about chemistry in the medieval Islamic world is the sheer quantity of manuscripts that deal with the subject. There are literally thousands that survive, dealing with subjects as varied as metallurgy, glass making, tile making, dyeing, perfumery, weaponry. There's even a description on how to distill alcohol. All this activity clearly points to a bustling economy, with consumers, soldiers, engineers, architects, all demanding innovation and all demanding new technology. A great example of applied chemistry in the medieval Islamic world was the manufacture of soap. This stuff, solid soap that you can really clean yourself with, was virtually unknown in Northern Europe until the 13th century, when it started being imported from Islamic Spain and North Africa. By that time, the manufacture of soap in the Islamic world had become virtually industrialized. The town of Fez boasted some 27 different soap makers. And cities like Nablus, Damascus, and of course Aleppo became world-renowned for the quality of their soaps.
A 12th century document has the world's first detailed description of how to make soap. It mentions a key ingredient, and it's a substance that became crucial to modern chemistry, an alkali.
Now, alkaline substances are crucial to soap making. But what's interesting is that our word alkali derives from the Arabic al-qali, which means ashes. That's because back then, alkalis were manufactured from the ashes of the roots of certain plants like saltwort.
Islamic chemists' new understanding of alkalis and other new chemicals gave another industry a lift too: glass making. The Islamic chemists discovered that they could change the color of glass using newly discovered chemicals like manganese salts. And they built industrial furnaces, some several stories high, to manufacture glass in huge quantities. The legacy of their skills can still be seen in beautiful stained glass windows. Islamic chemists also developed many other colors, pigments and dyes, using their new alkalis and metals like lead and tin. These helped architects to decorate mosques, like this one in the Iranian city of Isfahan, in a glorious range of colors and designs. Chemistry was also driven by the booming market in perfumes. In the main market in Damascus, traders still make up your favourite scent as they would have 1,000 years ago.
So it basically has a base of alcohol, and then he adds to it the oils from the plants that you want. Jasmine and rose water and mint. But these days they'll use...
Very nice. Yeah, I think I'll buy some of that.
Perfumiers pushed chemists to come up with ever more ingenious techniques for extracting subtle and fragile fragrances from flowers and plants. They responded by refining and really establishing a technique that all chemists would instantly recognize today: distillation.
Many of the techniques originate with Islamic scholars or even earlier.
Dr. Andrea Sella, a chemist from the University College London, shows me how distillation was used.
Distillations would have been done in devices sort of related to these. This is what's now called a retort, and we don't really use them anymore, but retort comes from the word to bend. In other words, a flask which has been bent over, and that's crucial. Well, many of the techniques...
The shape means that a gas produced in the flask is forced to condense in the spout, and it's the main way of extracting scents from flowers and plants.
Now, the idea here is that you heat at this end and you collect at the other. And so we should actually take a look and see if we can do a quick distillation with rose petals. First, we need to just put in a little bit of water. The water and steam will essentially control the temperature. What we don't want is for this to get too hot.
The trick with this kind of distillation is to use heat to release the scent molecules, but at the same time making sure that these delicate substances aren't destroyed in the process.
You actually use the steam to control the temperature, and the steam will carry those smells over. You can see the liquid coming up, condensing in the long tube. And there is already liquid coming over.
Through, yeah.
And that should be carrying with it some of the sort of rose water smell.
Yes, you can really smell it.
This picture shows a 14th century perfume distillery. Middle Eastern perfumes were known to have been sold as far away as India and China.
The Islamic chemists also played a pivotal role in another more gruesome industry: weaponry. Historical records during the Crusades talk in terrified tones of how the Muslims would attack the Christians with burning missiles and grenades, striking fear into the hearts of the defenders. Many of these use a substance known as Greek fire.
Islamic chemists improved on Greek fire by using and refining a naturally occurring resource: petroleum. They developed the idea of distilling petroleum, or naft, to create a lighter, extremely flammable oil, which they mixed with other volatile chemicals to make them burn furiously. And the result was clearly terrifying.
What all these medieval Islamic texts on chemistry have in common is their great attention to detail, which is clearly based on careful experimentation. In fact, the whole idea of a laboratory where chemical and industrial processes can be tried out really takes hold at this time.
The ingenuity of medieval Islamic chemists is impressive. But I wanted to know something deeper. What contribution did they make to our modern understanding of the principles behind chemistry? This is the centerpiece of modern chemistry, the periodic table. It lists all the known elements. Its key idea is to group substances with similar properties together. On the far right, for instance, are the inert gases. On the far left are the volatile metals. The periodic table is a triumph of classification, giving scientists a way of organizing their knowledge of the material world.
Classification is simply a way to think clearly. I mean, what you need when you have some ideas about how the world works is that gives you a kind of schema, and you chop the world up into categories. And that actually helps you to understand, to make sense of what's around you.
People have been trying to classify the material world since ancient times. The Greeks, for instance, thought there were just 4 worldly elements: air, earth, fire, and water. But this idea was a philosophical one and had little practical value. And that's what medieval Islamic chemists really changed. They used experimental observations to classify the stuff the world is made of. At the forefront of this was a medieval Islamic doctor and chemist called Ibn Zakaria al-Razi, who was born here in the city of Ray, just outside the Iranian capital Tehran, in 865 AD. Al-Razi's classification was very different from the Greek one. He argued, for instance, that minerals, roughly stuff we dig out of the ground, should be classified into 6 groups, depending on their observed chemical properties. The same guiding principle that lies behind the modern periodic table.
Now, what I've done is I've brought materials from his classification scheme. And we have here what he called the spirits. We have the metallic bodies, we have the stones, then we have the atriments, the salts, and finally the boraxes.
Each of Al-Razi's groups had a profoundly different experimental behavior. For instance, spirits were flammable. The metals were shiny and malleable. Salts dissolved in water. Of course, these classifications are not the way we do it today. But the point is that for the first time, Al-Razi was grouping substances on the basis of experimental observations, not philosophical musings.
We've come over 1,000 years since the work of Al-Razi. What sort of debt does modern chemistry owe to him for his classification?
Well, I think with Razi we start to see the first classification which really leads on to further experiments, the first schema which allows people to start doing rational work. And so really he lies at the start of almost formal chemistry, which ultimately leads to our periodic table.
I believe that what we see in the work of the Islamic chemists and alchemists is the first tentative steps to a new science. Yes, by our standards, it contained a lot of magic and mumbo-jumbo, but it placed an emphasis on experimentation that was truly revolutionary.
But bigger and better was to come, because Islamic mathematics and the experimental techniques of Jabir ibn Hayyan and Al-Razi were about to be welded together in a completely innovative way that would revolutionize their work and create the modern scientific age.
Until the 9th or 10th centuries, ideas about science and how the natural world worked were dominated by the Greek philosopher Aristotle, and they were very different from ours today. He believed that mathematics was concerned only with an abstract world of perfect forms, of idealized shapes like circles, squares, and triangles. It had no power to explain what we observe in the world around us, a world characterized by irregular, wonky shapes and constant change.
Physics is a Greek word meaning the science of change. And for the classical Greek tradition, there was a strong sense in which the science of change was in contradiction with mathematics. Mathematics dealt with perfect knowledge, with the unchanging world of mathematical forms. And it seemed in principle extremely unlikely that processes of coming into being and passing away, of growth and of decay, of qualitative change, could be captured with the beauties of geometry and mathematics.
The story of how humanity shook off this idea and began to see that mathematics is actually an incredibly powerful way of describing the world around us, is long and complicated. But for me, Islamic scientists played a crucial role, and I believe one man really led this movement to turn mathematics from a language of abstract thought into a truly practical science. He was, like me, from Iraq, and his name was Ibn al-Haytham.
What al-Haytham and his contemporaries argued for was the possibility, in a way, of a single science, which would be both mathematical and philosophical, which would link together a physics, a science of change, with a mathematics, a science of quantity. And that seems to me to be radical and crucial for the construction of new forms of reliable knowledge.
Ibn al-Haytham was born in 965 AD in the southern Iraqi town of Basra, and other scholars regarded him as a prodigy.
He shot to scientific fame just after the turn of the first millennium and was an incredibly innovative and brilliant scholar. His reputation as an intellect spread throughout the empire. But it was this reputation that would almost cause him to lose everything when he took up the poisoned chalice of trying to tame one of the world's greatest rivers.
There's a wonderful, if suspiciously apocryphal story about how Ibn al-Haytham's career as a scientist was transformed. It concerns the Nile and how, just after the turn of the millennium, Ibn al-Haytham was asked by the ruler of Egypt to find a way of controlling it. Could he prevent its unpredictable and potentially devastating floods and droughts? But it didn't take Ibn al-Haytham long to realize that the Nile was way too large to control. On hearing this, the Caliph flew into a terrible rage and ordered Ibn al-Haytham's execution. Ibn al-Haytham responded by feigning madness. The execution was called off and he was placed under house arrest. There, with time on his hands to contemplate, the story goes, Ibn al-Haytham considered deep and fundamental questions in physics. And he began with a truly enigmatic and universal problem. He asked if the wonderful and entirely mysterious nature of light and vision could be explained by mathematics and geometry. Under house arrest, or perhaps here in the rooms of Al-Azhar University in Cairo, Ibn al-Haytham carried out a series of experiments that created the modern science of optics. I'm with Dr. Al-Bizri, who has carefully studied Ibn al-Haytham's work. He explained that Ibn al-Haytham first considered the Aristotelian explanation for how we see, an explanation that was completely unmathematical. Aristotle argued that when we look at, say, a tree, its essence or form emanates from it and then mysteriously flows into our eyes.
So if I'm, for instance, now looking at the buildings and the trees on the banks of the Nile, I'm receiving the forms of these buildings and these trees in the eye, abstracted from their matter.
According to Dr. Al-Bizri, Ibn al-Haytham found this idea deeply unsatisfactory. He wanted a mathematical explanation. And looking back at existing Greek writings, he found one, although it was obscure and bizarre. This idea claimed that we see because light rays come out of the eye.
Ultimately, it says that vision occurs by way of the emission from the eye of light that is shaped in the form of a pyramid or a cone.
This cone-shaped beam illuminates what we're looking at and is defined by nice geometric straight lines. It seems Ibn al-Haytham liked this mathematical approach, but immediately spotted its flaws. If we see, he asked, because light comes out of the eye, why does it hurt when you look at a bright object like the sun, but not hurt when you look at something dim? Or at night, can light from our eyes really be lighting up distant objects in the sky? So, in an inspired piece of thinking, Ibn al-Haytham combined the two Greek ideas and defined our modern understanding of light and vision. Light, he said, does travel in straight lines that obey geometric laws, but instead of them coming out of the eye, these rays travel into it.
It is the development of an entirely new theory, and also methodologically, it is the beginnings of mathematizing physics.
What Ibn al-Haytham did was take the principles of geometry with its rules governing straight lines and apply them to the real world. He then designed experiments which would test whether the real world measured up to his mathematics.
In about 1020, Ibn al-Haytham published his groundbreaking geometric explanation of light in his Kitab al-Manadhir, or Book of Optics. And what really marks this book out as science is that Ibn al-Haytham carefully justifies his theories with detailed experiments that others can repeat and verify. He starts from first principles to find out how light travels.
For his first experiment, Ibn al-Haytham wanted to test the idea that light travels in straight lines. Now, to do this, he took a straight tube on which he'd drawn a straight line down the side, and a ruler, again with a straight line down the length of it. And by matching the two together, he was convinced then that the tube was straight. Now, if he uses it to look at an object, in this case a candle, he can see the candle through the tube, which is good evidence that the light is travelling up in a straight line. But just to be sure, he then blocked the end of the tube. And then, by looking at the candle again, of course, he can't see it, because what this does is confirm that the light doesn't travel to his eye via any other route in a curved path outside the tube, proof that light only travels in a straight line. Now, this might sound quite trivial and obvious to us, but Ibn al-Haytham was starting from first principles.
Then, through experiment, he extends his light travels in straight lines idea to many other phenomena. He explains how mirrors work by arguing that the angle the ray comes in at is the same as the angle it bounces off at. He explains what we now call refraction, why objects look kinked in a glass of water, arguing that light rays bend when they move from one medium to another. And then he tackles the nature of vision.
Ibn al-Haytham wanted to understand how an object makes an image on the retina of the eye. So he built what he believed was a stripped-down version of the eye, which is basically a black box with a tiny hole in it. This is what we call today the camera obscura. He next took his subject, in this case Anna, who's very brightly lit, and we now go inside the box to see what the image looks like. Now that I'm inside the camera obscura and I've allowed my eyes to get used to the dark, we can open the hole. And there we clearly see the image of Anna waving on the screen. But the image is inverted because light travels in straight lines, and so the light from her head has to move diagonally downwards to hit the bottom of the screen, and light from her feet travels diagonally upwards to hit the top. But more importantly, what this proved to Ibn al-Haytham is that there's a one-to-one correspondence between every point on the object, on Anna, and every point on her image on the screen.
Just like a modern scientific paper, the attention to detail in the Kitab al-Manadhir is incredible. His book isn't just a dry scientific treatise, it's a manual for future generations.
In his work, he constantly justifies his theories about light with experimental observation. And he describes his experiments in great detail so that other people can repeat them and confirm his ideas. His message is, don't take my word for it, see for yourself. I believe that Ibn al-Haytham was one of the very first people to ever work like this. This, for me, is the moment that science itself is summoned into existence and becomes a discipline in its own right.
What I find so impressive about Ibn al-Haytham is how once he arrives at his mathematical theories, he then uses them to extend our knowledge of the real world. So, for instance, he used his new ideas about light to deduce that the Earth's atmosphere is of a finite thickness. And he even estimated what that thickness is. He did it basically by measuring how long twilight lasts. He rightly assumed that the reason it continues to be light after the sun has dropped below the horizon must be because its rays bend as they enter the Earth's atmosphere. The length of twilight and an educated guess for what we today call the air's refractive index gave Ibn al-Haytham a way of estimating the thickness of the Earth's atmosphere. He came up with a figure of around 40 kilometers, about half of the modern value. That's pretty impressive. It really shows how mathematics extends the power of science to explain. On my journey so far, I've been overwhelmed by the sheer intellectual ambition of medieval Islamic scientists. When their leaders asked them to find out the size of the world, scholars like al-Biruni used mathematics in startling new ways to reach out and describe the universe. And as trade and commerce boomed, scientists like Al-Razi responded by developing a new kind of experimental science, chemistry. But if there's one Islamic scientist we should remember above all others, it is, in my view, Ibn al-Haytham, for doing so much to create what we now call the scientific method.
The scientific method is, I believe, the single most important idea the human race has ever come up with. There is no other strategy that tells us how to find out how the universe works and what our place in it is. Of course, it's also delivered technologies that have transformed our lives. So the next time you jet off on holiday, or use a mobile phone, or get vaccinated against a deadly disease, remember Ibn al-Haytham, Ibn Sina, al-Biruni, and countless other Islamic scholars 1,000 years ago who struggled to make sense of the universe using crude mirrors and astrolabes. They didn't get all the right answers, but they did teach us how to ask the right questions.
In the next episode, I travel to Syria and northern Iran to find out about the great Islamic scientists who revolutionized astronomy, making it a truly modern science. And I'll also discover how the man many consider to be the father of the European scientific renaissance, Copernicus, borrowed from Islamic astronomical theories. And I'll unravel the mystery of how the golden age of Islamic science came to an end.
And that final episode of Science and Islam is here at the same time next week. Jerry Robinson is here with another Moneymaker next tonight on BBC4. And on Radio 3 now, Donald MacLeod explores the work of Handel, this week's Composer of the Week.